work on a big problem. So tonight's homework, like you're starting with matching, and then you're finding all the pieces of the information by completing the square and graphing it. Tomorrow we will do the opposite, where you're given the information, like the vertices and the foci. You come up with the equation, but tomorrow is also like the summary day of pulling all of it together. So we'll talk about eccentricity, which gives us like how wide or narrow the conic is and how that actually forces the conic to be a circle, a parabola, a hyperbola, or an ellipse. So the eccentricity would actually describe the type of conic we have. But then we'll also look at the expanded form when it's equal to 0 and why just by looking at the expanded form we can decide the type of conic without doing any work. So no work necessary. By looking at the equation, you can kind of tell the conic that you're looking at. So that'll be like you tomorrow kind of identifying and working on just how can we quickly know the conic that we're dealing with. So today we have a hyperbola, which we've graphed hyperbolas this year in chapter 2, and you graphed hyperbolas last year in chapter 8, just like the parabola. So the algebraic hyperbola goes along with this equation, that 1 over x. And we just graphed these back in chapter 7, so we actually just graphed them again. Grace, I think you were the one who told us or remembered what these look like. Yeah, so like this here, and this here. And hyperbolas have what in them, Grace? Asymptotes, yeah. So our hyperbolas, just because they're geometric, are still going to have asymptotes. But our asymptotes are not going to be horizontal and vertical lines. So it's not just going to be at x equals 3 and y equals 7, or whatever the numbers happen to be. In this case, they're both 0. But there will still be asymptotes in the graph. These pieces are called branches. So like there's similarities to the function versus the conic, just like the parabola has similarities with the parabola function and the conic. But there are going to be differences as well. But we've graphed these before. They have a lot of similarities. So our conic for the hyperbola, same definition that all of them start. The set of all points. That makes it a locus. That then meets a certain geometric property. And that property says the difference, there we go, of whose distances from two distinct points, called foci, is constant. Does anybody remember what the word was here for an ellipse? Just one tiny switch of a word changes it from a hyperbola to an ellipse. It would be the sum. So for an ellipse, it was the sum of the distances from two foci. For a hyperbola, it's now the difference. So I'm going to make just that little sketch up here just to kind of see what the definition is talking about. So this says that any point on one of these branches, wherever your point happens to be located, so I'll pick a point right here, we have two distinct points called foci. Those points are in the mouth, as I call it, of the branches. So they're always inside, whether it's inside the ellipse, inside the one parabola, or in this case it's inside those two branches. So if I take the distance to get from one focus, I'll call that distance 1, and the distance to get to the second focus, which we'll just say is distance 2. It's saying if you this time subtract those differences, or those distances, then that value is constant. Constant means it's the same no matter where you are on the hyperbola. So if I subtract the distance from the point to my focus, the point to the second focus, that distance would be the same right here where I have my value located, or it could be down here where my point would be located. But as long as I'm on one of the branches, the difference would be the same no matter where you are. Even if you're really far away, that difference is still going to be the same. Could you do positive or negative? You're always going to take the longer one minus the smaller one. So it would always be the longer distance minus the shorter distance. And then underneath it does say each hyperbola has two disconnected branches, so that tells you that they will never connect together. They will always be going in opposite directions, which is the same thing with the hyperbola in the algebraic sense. You have these two branches that are going in the opposite direction, always kind of like diagonal from each other. So we are going to look at identifying 5 different parts of these hyperbolas. So we're going to look at the transverse axis, similar to the major axis. We're going to find the center of the foci and the vertices, those three things identical to an ellipse and a hyperbola. And then we're going to identify the conjugate axis, similar to the minor axis. So like a lot of similarities, they have pieces that are the same, just different names. Because it's a hyperbola, it's not an ellipse. So we'll start with horizontal on the left, vertical on the right. Make yourself a large, neat picture, neat-ish. So a transverse axis. So looking at the things we're asked to identify, it says the transverse axis is the segment connecting the vertices. It's also the segment connecting the foci. So the center is the midpoint of the transverse axis. So we have this axis, which is that important axis where everything lies. And that is going horizontally. So I'm going to make just like a horizontal dotted line here. Everything is going to lie on this transverse axis. Almost like that line of symmetry that cuts through the graph. So we have a focus at each end. And the center, as it says, is in the middle. So the center is in the middle, just like it is for the ellipse. What's the distance from the center to the focus? Brandon? That's C. It's still C in an ellipse. It's still C in a hyperbola. C is the distance from the center to a focus. Brandon?
And the vertex are closer to the center than the focus.
Yeah, so now each vertex is actually closer to the center than the focus is. So it's going to be in between somewhere in that distance from the center to the focus. Your vertex would be in that location. So we'll just put it here. And Brandon, that distance is A. Yeah, that's the same. So from A to a vertex, or the center to the vertex is A. And again, that whole thing is called the transverse axis. So my transverse axis is horizontal, where all of the information lies is horizontal. So there was the other letter that we used. We have the A and the C. Virginia, that other letter was B. And if I go down below, I now have the transverse axis, the line segment kind of connecting everything. We have a center, we have a foci, two foci. We have vertices, and then we have this conjugate axis. That's the B value. Now, of course, it doesn't have specific endpoint values, but if we go in the other direction, that's going to then get us the width of the parabolas or the branches so that we know how wide or narrow they would be. So going from the center up a distance and down a distance makes this conjugate axis. And that value is B. So this distance here is B. So B still goes the opposite direction. A and C are one way, B gets us then the other. So we know how wide or narrow the parabolas are, or the branches are. Questions? So I need to draw some branches. Sure? Yes. Okay. So if you go from your focus, we'll have two branches going opposite directions. They're disconnected. They open toward the focus. So the other vertex open toward the focus. And we'll talk about how to determine how wide or narrow they will be. Because of course you can't just draw random ones like we did now. Brandon.
This might be going a little bit ahead, but does eccentricity work where if you take c divided by a, it
Mhm.
is greater than 1, it's a hyperbola, less than 1, it's an ellipse, and equal to 1, it's a circle?
Close. You're right with the first two.
What did you said B was for how wide the circle is, but it's not doing.
We need it, yes, because then I know, like, will the branches be really wide or will they be really slim?
How do you tell that?
We will. I promise we'll be okay. I've never led you astray out of, like, I don't know, how many years or how many days have you had me at this point? 182 last year, maybe? And we're at 150 maybe? 145? Yeah. You've had me a lot of days. I'm so sorry for all of you. Except for Kayla. She's like, I'm the lucky one. Only had her. Oh, and Michael. Yeah, only like 140 so far. Kate's like in the middle. The three of you are lucky. You have dealt with me all this time.
What?
All right, so Chelsea, if we have a horizontal hyperbola, how do you think we find the vertices?
H plus C or H plus A.
Or minus.
Yeah.
And then,
K.
and the foci.
H plus or minus C.
And then, okay. Same formula. I'm not asking you to memorize anything new. Same thing. It's just they're inside the foci instead of being outside. So foci are going to be the longest distance. So if you just take your graph, rotate it 90 degrees so that it goes up and down. We'll make a little vertical transverse axis. So transverse axis is that axis where the information, the important information lies. Again, we have the focus at the top and the bottom, the center in the center, that midpoint. And from the center to one focus is still C. And then we have a vertex somewhere between the center and the focus, the same distance above and below. And that's A. So that is our transverse axis, where everything, all the important pieces lie. The other axis is that conjugate axis that then helps us determine how wide or narrow those branches are, and that's B. So again, we will look at that information. We'll talk about why that distance for B is important to actually create the branches. So Eris, the vertices would be, if it's vertical,
H equals K plus or minus A.
and the foci.
H and K plus or minus C.
Any questions? All right, so underneath there, we have, of course, our standard form. Start on the left, still go the horizontal, so that you have them right below, and the vertical. Who remembers what the form for the ellipse would be? Brandon, what's the ellipse?
It would be x squared over a squared plus y minus k squared over b squared equals 1.
Okay, so that's the ellipse. How do you think the hyperbola changes? Look at the definition. How how do you think the equation for the hyperbola would change, Chelsea?
Instead of a plus sign, it's a minus sign.
So instead of a plus sign, it's a minus sign. Because it's the difference of the distances instead of the sum of the distances. So with an ellipse, wherever the bigger number was underneath, like the x or the y, that told us the direction. So a horizontal ellipse had the biggest number underneath x. This time, it doesn't matter which one of those is bigger. The important part is the term that's positive. So if x is positive, or if x squared is positive, then it's horizontal. So it's a horizontal graph when x squared is positive. So we're going to now be focusing on the part that is positive, the term that is positive. Kate?
Won't x squared always be positive?
It will not, because in the vertical one, the y goes first, but it's still a squared underneath. So now this time, like the a and the b values aren't flip-flopping. It's the actual term that flip-flops. So now x, the whole term for x has the minus sign. So not in the middle, like inside the parentheses, but that whole term. So this piece here, that y squared term, is positive. So a lot of similarities between the two. There's one other tiny little difference, and that's how we find the c squared term. Because the foci are the furthest, Brandon, it has to be a squared plus b squared. And that gets them then outside of the vertices instead of inside the vertices. Questions? Richard? You know what? I mean, you are finding the distance of two things, yeah. But it's not the Pythagorean theorem because it's not a right triangle. It just happens to match with that same pattern. Other questions? So we have to talk about one more thing. As I said, each one gets a little more detail. There's one part that we haven't talked about, and that's those lovely asymptotes. Because we still have to be able to find them because the asymptotes are what creates the branches. So the branches are actually created from the asymptotes. So we're going to talk about finding those, and that's the last thing we have to go over. So if you look at the top of the next page, each conic just kind of adds another piece. That's the evil thing about conics. It starts off easy. I got a circle, so warm and friendly. And then you keep adding all these extra little pieces. So it says, as you move out on the branches of the hyperbola, the branches approach asymptotes. So that kind of creates the width or the narrowness of the branches. We're going to draw two more basic little graphs because I want you to physically see how the equation is created for the asymptotes. And it just makes more sense if you have a picture to look at. So one last time, horizontal versus vertical. I'm just drawing a real basic graph this time. So we're going to have these two branches going horizontal. In the middle, we have a center. And then we have those vertices. Not even drawing the foci, because they're not really involved in the graph when it comes to trying to get the asymptotes. So the distance from the center to one vertice is A. Going the other direction, so A goes horizontally, since it's a horizontal graph. The B has to go vertically. Above and below, that distance is B. So these guys are kind of like connected together. The way we create the asymptotes is actually to make a box by graphing two horizontal lines through the upper point and the lower point of B 2 vertical lines through the points of the vertices. So we're going to create a box. So making a little box. That was supposed to go through the vertice. Your asymptotes will go through the center of your hyperbola and the corner of the boxes. So the width of the box kind of helps create then that asymptote, and it'll go directly through the corner. So through the center and the corner, I usually draw these in dotted. I'm just drawing them in as solid lines so that we can kind of see them. So they should go through the center and the corner of every piece of that box. So the upper corners, the bottom corners, all 4 corners creates our asymptotes. We actually draw the asymptotes first and the branches last, so that then our branches can skim along the asymptotes. So the way we find this equation, usually an equation is in what form? For a line. So these asymptotes are lines. What form is a line usually in, Brendan? Y equals mx plus b. But that's when the line starts at the origin and moves from the origin, because that's the y-intercept is. We don't have an origin, we have a center. So our line starts at the center. Now, the center has an h and a k value. So we're going to start with the k value because that's our b, that's our y-intercept. And I have 2 lines, one with the positive slope and the same negative slope. So that gets a plus or minus. Because you have 2 lines that have the same slope, just one's positive, one's negative. What is the slope of that line, Virginia? Yeah, because it's rise over run. So we're going up B over A to get the next point on that line, which is the corner of the box. So B over A. And then to know how far we're moving left or right, that's where the x minus h comes in. So it's similar to point slope form. We did point slope form a little bit in the chapter P in chapter 1 at the beginning of this year. We did point slope form a little bit last year in chapter 2. Both of those are at the very beginning. So we have the height, kind of like the pseudo y-intercept, that's k. Plus or minus because it's 2 lines with the same slope increasing and decreasing. And then that x is moving left and right with h. Questions? So graphing vertically real quickly here. So there's my 2 branches in the middle, going up and down. Again, to get to the vertex, it's A. Going left or right, that distance is B. And then we would create this little box. So really, we should create the box first before we graph the branches. Because the asymptotes guide a graph. They're grid lines for you to follow graphically. So our asymptotes go through the corner of the box. How do you think the equation changes when it's vertical? Brendan?
Y equals H, K,
Still K, yep.
plus or minus A over B.
And then
X minus
x minus h. Slope is always with x, like mx plus b. So the slope is always attached to the x. The x has that minus h with it because our graph is no longer starting at the origin 0, 0. It's starting somewhere else. So the hope is that you might not need to memorize this. If you can really just look at the graph and rely on the graph. Like looking, once you have that box drawn, you'll be like, okay, well the height of my box is 3. The width of my box is 4, so rise over run would help give the slope as well. So really, like a lot of it, if you rely on the graph, you should be able to kind of find all of the pieces as well, instead of like thinking, do I have to memorize all these formulas? Yes, if you like memorizing formulas, go for it. But if you're a visual person, you can look at the graph and then kind of get those pieces from the graph as well. So we're going to go through a problem, just one, where we can try and complete the square. We're going to sketch the graph and find hopefully all the important parts as well as the asymptotes. That would be that new piece of information. So if you look below, what would you do to complete the square? Do you have to do anything with the y's?
No, you just keep
Yeah, so it's just a single y squared term. It's a negative 3y squared. There is not another y with it, so we'll just keep it there. So Nick, what number do we put in to complete the square? A 1, but on the other side, a 4. And then we factor that perfect square trinomial, combine the left, and we get a negative 12. What do you need to do for it to be in standard form? Chelsea?
Divide by the negative 12.
Yeah, we have to divide by negative 12. It's okay that it's negative. It doesn't always have to be positive, especially now that I have negative signs in the problem. When you divide, the positive term goes in front. Which term would be positive, Brandon? Right, the y squared.
And please pardon this interruption. Attention seniors. Senior prom tickets will be sold for 3 days only, starting tomorrow, Wednesday, April 10th through Friday, April 12th, during homeroom and in the athletic and activities office throughout the day. The cost per ticket is $85, cash or check. Checks should be made payable to North Hills High School. All tickets must be purchased by a North Hills 12th grade student, and
What
all
direction
North
does this
Hills
go?
students attending must have a dance agreement and permission form completed
Which term
in
is
order
first?
to purchase a ticket. All this information
Vertical.
and forms can be
So
found
right
in
here,
your Gmail
y is
inbox
first, so
or
it's
in the
vertical.
athletic and activities office. Hard copies of this
A squared is
information
always
was
on the
distributed
left,
in your
b
grade
squared is
level English
always
class.
in the right denominator.
Extra copies
So that means
are
A is
are
2,
available in the main office.
b is the
Thank
square
you.
root of 3. C squared is now adding those two together. So c would be the square root of 7. So again, the first term, whatever is positive, tells you the direction. Y is our vertical variable. So if y is positive, we're moving vertically. If x is positive, you're moving horizontally. It doesn't matter which one is bigger. It's what's positive in the front. Questions? All right, so we need a center so that we can graph this hyperbola. Eris, what's the center?
Not positive. Right.
Opposite.
Yeah.
So opposite would be
Just one.
negative 1? Because it is a positive 1.
Yeah.
And the y value is
0.
a 0. So then to get the vertices, here's A. A is 2. The vertices would go from the center, moving vertical with that distance of A. So H is negative 1, 0 plus 2, 0 minus 2. The foci are H, K plus or minus C. So H is negative 1, K is 0, C is the square root of 7. So 0 plus or minus the square root of 7 would just be plus or minus the square root of 7. So we're going to graph this. We're going to see if we can quickly plot some points. Try and use the graph. Hopefully you still have some space. Or if you grabbed graph paper when you came in, you should have some graph paper. You only need 5 or 6 spots on that graph paper. Totally up to you. So the center is at negative 1, 0. A is 2. So if I go from my center up 2, that gets me that negative 1, 2. Down 2 gets me the negative 1, negative 2. That's my A. Now I'm going to go alphabetical. B goes the opposite direction. That's the conjugate axis. And it's the square root of 3, which is a little less than 2. So going back to the center, a little less than 2 to the left, a little less than 2 to the right. Now I'm going to make a box. So my center should be in the middle. I'm going to connect those 4 points by 2 horizontal lines, 2 vertical lines, making a box. So horizontally up at 2 and down at -2, and then going vertical through those p values of the conjugate axis. And then you're going from the center to each corner of the box that creates your asymptotes. So we have these 2 asymptotes going through the center and each corner of the box. When you go to graph your branch, you're taking your vertex and skimming along the asymptotes. Your vertex skimming along the asymptotes. And then the last thing were the foci points, which were up the square root of 7, which is a little less than 3. So from the center, up a little less than 3, down a little less than 3. They should be outside of the graph, beyond the box. Questions? So if you're looking at the graph when you're trying to write your equation, we need a y-intercept, which is really not a y-intercept because it's like that starting y value. Well, the middle of my box is starting at 0, so technically there'd be a 0 there. It's the y value, the k value. The slope is rise up to, run the square root of 3. Don't rationalize it. Then you can't see your rise over run. It's probably the first time I said that all year. Don't rationalize. And then it's moving, x is moving right, I'm sorry, left 1, so it's x plus 1. So instead of the origin, I'm using that center point in the equation. You don't need the 0 there, I just put it there and see that it usually has the same.
I feel like if you don't rationalize it, if it was rationalized, the 2 square root of 3, would that also be right as a line? So for every 3, it would go up 2 square root of 3. For every 3, it would go up 2 square root of 3.
Well, 2 squares of 3 is going to be at the top.
Yeah.
So it's going up 2 squares of 3 and over 1. Yeah, it's just going to get you a point higher up, not in the corner of the box. So it wouldn't directly correlate with like the box. If easier, you just if it's 1 uniform line. Have a great day. So it's a parabola because the distance from the center